Today we have a very special guest, Professor Charles Townes. He's come to us today from UC Berkeley, and he's going to be talking about science in his life and the potential of discovery. Charles is a South Carolina native, and he was educated at Furman University in South Carolina and Duke, and did his PhD at Caltech. He worked on radar systems during the World War II, and after World War II went to Columbia and Bell Labs, where he did the work on masers and optical masers and what eventually became the laser that earned him the 1964 Nobel Physics Prize. And after Columbia, Charles went to MIT. And after MIT, he went to UC Berkeley, where he is working today on CO2 lasers and looking at stars and the life cycles of stars using heterodyne techniques with CO2 lasers. So if you'll join me in welcoming Professor Townes.
Thank you. It's a pleasure to be here with you today. I'm going to talk about discovery, the puzzles of discovery, and how really new things are surprising, and much of society is sort of against them and thinks, no, it can't happen, and so on. And I'm going to talk about it in a personal way to sort of show you, because you have to see these things personally in order to really believe just what happens, and tales of what happens. After they've discovered and become very popular, whatever, well, yes, of course, that's obvious, but before that, who knows? Now, after my PhD at Caltech, I went to Bell Labs. I wanted to do science there, and it was a good place. There was no jobs in universities at that time, and during the Depression years. So I thought, well, Bell Labs is a pretty good place. But then immediately after that, the war came along, and I had to go into engineering and do radar. But I had a lot of good friends there, a lot of good people. Bill Shockley was there, and Bill Shockley, right after World War II, he tried hard he wanted to make a transistor. The transistor word wasn't real at that time, but he wanted to try to amplify with semiconductors. And he tried it, and he got somebody to help him. Didn't work. So he gave up and said, well, I guess it's just not practical. Now, how did the transistor come about? Well, Walter Bratton was at Bell Labs at that time also, and a good friend of mine. Walter was trying to examine the characteristics of oxides on copper, the conductivity through oxides on copper, just making experiments on that. He found a very funny effect. What in the world is going on? This was peculiar. And he went to John Bardeen, who was there, and a theorist, a physical theorist, and what's happening here? I don't understand this. And John looked at it and said, hey, you've got amplification. Then Bill Shockley jumped in, and the three of them together produced a transistor. But it's a complete surprise. Now, during World War II, I was working on radar, and I worked on radar in about 1 centimeter wavelength, and the radar failed. Why? Because we discovered the water vapor line in the atmosphere had absorbed those radar waves, and so they couldn't work. Oh dear. But what did that do to me? I said, well, now wait a minute, the water vapor absorption line, maybe we can do spectroscopy at microwave frequencies. And I went out to Caltech with a professor of mine, I.S. Bowen, a very famous optical spectroscopist and so on. I said, I think maybe I can do spectroscopy in the microwave region. What do you think is the best thing to do in spectroscopy in the microwave region? Bowen looked at me and said, radio waves never been any good for spectroscopy. Just forget about it. It's just not going to work. No good. Well, I was sure he wasn't quite right, and I went back to Bell Labs. They let me work on it, and examined ammonia and began to get spectral lines. And sure enough, we got very high spectral resolution. And so I could determine the shapes of the nuclei within the molecules. Not only the structure of the molecules, but the shapes of the nuclei and the spins of the nuclei, and became a very important field. And I have just signed somebody's book on microwave spectroscopy now that I wrote as a result of all of that. It became an important field. And as a result, I got a job at Columbia University. They weren't interested in molecules, but they were interested in nuclei that I was finding out about, and I got a job at Columbia University. Now, at Columbia University, I was, again, working away at microwave spectroscopy, and I wanted to get to shorter wavelengths. With electronics, we could make waves down to maybe a couple of millimeters in length. We couldn't get any shorter. I'd like to get down below a millimeter, down in the far infrared at least, and so on. I kept working and trying to figure out how to do this and tried various things. And I was appointed chairman of a national committee to try to examine how to get shorter wavelengths. And we traveled all around visiting laboratories. We traveled to Europe, and nobody had any ideas. The last meeting of our committee in Washington, I woke up early in the morning worried about it. We hadn't been able to get anywhere. It was before breakfast, so I went out and sat in the park on a bench and thought about why I haven't been able to think of an idea, and thought through it and said molecules, of course, atoms and molecules can produce short waves, but they can't amplify. And why not? And well, because of thermodynamics. Hey, wait a minute, they don't have to observe, they don't have to agree with thermodynamics. We can make them non-thermal, put more of them in the excited state than the lower state. And you got, hey, wait! Oh boy! I wrote down some notes quickly on a letter envelope I had, notes and figured, put some numbers. And yeah, it looks like it might work. Well, I didn't tell anybody at the meeting about it. We just closed the meeting and wrote a report saying nobody could see how to do it. And I went home to Columbia, and I persuaded the student Jim Gordon to do this as a thesis. Well, we'd been working on it for about a year and a half, and the chairman of the department, Polycarp Cush, who got a Nobel Prize, and the former chairman, Isidore Rabi, who also had a Nobel Prize, they both came in to see me and said, look, Charlie, you've got to stop. That's not going to work. That's not going to work. You know it's not going to work. We know it's not going to work. You're wasting the department's money, and you've got to stop. Well, fortunately, I was an associate professor then. They couldn't fire me. Couldn't fire me unless I did something morally wrong, that is. They couldn't fire me just because they thought I was mistaken. And I said, no, I think it has a reasonable chance. I'm going to keep going. Well, they marched out of my laboratory angrily and so on. Well, about 3 months later, we had it working. Wow. Jim Gordon came into my classroom. I was teaching, and he came to my classroom. Hey, it's working. So we all dashed out and went to the laboratory, and this thing was working. Now you see the negativity that new ideas can produce. New ideas are new, and many people won't believe them, and that's the most revolutionary things. They're frequently the things that people don't know at the moment, and they don't understand, and they don't want to believe because they haven't thought of them themselves. Maybe that's the reason. Well, we call this the measure for microwave amplification by stimulated emission of radiation, and it amplified microwaves and gave a very, very pure frequency, and I could make a time standard out of it and so on. Well, Niels Bohr's son was a postdoc at Columbia, and I knew him, and I was visiting Denmark, and he invited me to his house, so I met Niels Bohr. Some of you probably heard of Niels Bohr. And he said, well, you know, what are you working on? I said, well, I'm working on this thing, amplification with molecules. We've got very, very pure frequencies. Niels Bohr said, oh no, that's not possible. No, they're in this cavity for a finite time, and they can't have pure frequencies. They can't have such pure frequencies. You know, the uncertainty principle. I said, no, we've got to be pure. Oh, no, something's wrong. You don't understand. And so he never believed me. A little later, I was at a cocktail party in Princeton, and John von Neumann, who was at the Institute for Advanced Study, was there at this cocktail party. And he said, as you know, you're usually one scientist to another. John von Neumann was a very famous mathematician and theoretical physicist also. And he said, what are you doing? I told him, well, we had this new kind of oscillator at a very, very pure frequency. Oh, no, that's not possible. Oh, no. New idea, difficult. Well, I told him, no, it's working, and he went off and got another cocktail. About 15 minutes later, he said, hey, you're right, let's talk about it. Got excited. Well, now, mesas then became very popular. I worked on my laboratory for about 2 years before they worked. A lot of people came by and thought, oh, yeah, interesting idea, and nobody competed with me. Nobody else was trying to build one. So we made it work. Once it got working, then it was very exciting, and everybody got excited about it. And a lot of industries hired students who'd worked in this general field of microwave spectroscopy and so on. They went to industry, and so the industry became very full of mesas then, and because they made the best possible amplifiers, very good frequency standards and so on, exciting new field. But nobody thought they'd get to very short wavelengths. We made it work first at about 1 centimeter wavelength using molecules. I thought, well, I'd try to make the idea work there first because I had all the equipment for that frequency, and that was the easiest thing to do. I wanted to get to lower frequencies, higher frequencies rather, lower wavelengths. And I thought about it. I'd like to get down I'd like to get down the infrared. Well, everybody said, oh no, that can't be done. That's too bad, but no, I can't do that. So I thought about it and wrote down some equations. Hey, looks like we can get right on down to optical frequencies. Equations say so. We should be able to get down to optical frequencies, all right, with an resonator and optical frequencies. And Art Shuttle, who had been a postdoc with me and married my kid sister, he was at Bell Labs. I was consulting with Bell Labs and went and talked with him about it. Said, well, I've been wondering about that. Could we work on it together? So we did. And he had the idea of making a resonator with just 2 flat mirrors. He had worked with a Fabry-Perot doing spectroscopy and 2 flat mirrors. Oh yes, that makes a good resonator, just light going right straight back and forth. Oh, great idea. So we gave a patent to Bell Labs, and Bell Labs patent lawyer said, oh, light's never been used for communications. I don't think Bell Labs would be interested in it. If you want to patent it, you just take the patent and go ahead and have it yourself. Well, I told Art, look, just because they don't understand, we shouldn't cheat Bell Labs out of this, because you were working for Bell Labs and I was consulting, and I thought it probably ought to belong to Bell Labs. You go tell them it can work for communications. He phoned me up next week and said, well, they say if we can show how it can be used for communication, well, then they'll patent it. So we did. So we wrote a patent, optical mesas and communication. Well, I knew by then, everybody was so excited about the field of mesas, I knew that if I started working on it and try to make one work, and I'd have a lot of competition. So I decided with Art that we should just write a theoretical paper about how to do it, and then everybody would jump in and try to do it, and that's just what happened. We wrote a theoretical paper, and it was the first paper to show how to do it, and then everybody jumped in and started working on it. And Ted Mayman, in the industry, built all the first lasers. Ted Mayman was the first one. He was in industry, and I know a lot of others in industry. And Ollie Javon, one of my students at Bell Labs, he built the first gas laser and so on. So the field grew very rapidly after initial doubts. But now, let me give you a few other cases. Arnold Pen was one of my students at Columbia University. And I suggested that he look for hydrogen in interstellar space. First place, I had looked for ammonia in interstellar space, and I came out to Berkeley, thinking I'd look for ammonia, and in interstellar space, because ammonia was a nice molecule with good strong lines in the microwave region, and I looked for ammonia. George Field, who was then chairman of the Department of Astronomy at Berkeley, And a good, outstanding theorist, George Field, said, "Oh, look, ammonia can't be in interstellar space. I can prove theoretically that you can't have stable molecules out there. I can prove that theoretically. You're crazy to waste time looking for it that way." I said, "Well, no, I won't look for it." Well, Jack Welch, and one of the people who helped me, he was an electrical engineer and doing radio astronomy, and I worked on it, and there it was. We found ammonia, the first stable molecule in interstellar space. And now, I don't know, about 75 or 80 different molecules have been found, some of them biological in nature. That is, the kind of molecules that are used in biology, complex carbon molecules and so on. A lot of molecules in interstellar space. And it's become a very big field. Again, you see, nobody wanted to do it because they couldn't be there. But I took a chance. Well, Arnold Pen, I suggested to him that he look for hydrogen in interstellar space. There's a hydrogen fine structure in interstellar space. Now, the hydrogen fine structure I knew about because when I was at Columbia, Professor Lamb had measured the fine structure of hydrogen and tried to measure it accurately. Well, what's the point in doing that? Well, just to make an accurate measurement. He made a measurement. He found it wasn't what people expected. There are some particular nonlinear phenomena associated with the electron being very close to the nucleus, and he got a new phenomenon. So he found a new thing. He got a Nobel Prize for that, you see. Just surprising. Well, why do it? Well, just measure it more accurately and see what's there. And something surprising was there. This fine structure, I thought, well, let's look for it in outer space and see if we can find hydrogen out there. And so Arnold looked and he worked on it. He didn't get it, but he did enough interesting work that he got his, could write a thesis, get his degree, and he went to Bell Labs. He got a job at Bell Labs. He kept looking, using masers as amplifiers. We had developed masers, and he knew about masers, using masers for very sensitive amplifiers, and looking in interstellar space for hydrogen. He didn't find it. What did he find? He found the origin of the universe, the Big Bang, the radiation. He found some radiation up there nobody expected. Continuous radiation in the microwave region, which was the remnants of the initiation of the universe about 13 billion years ago. Discovered the origin of the universe. Again, he got a Nobel Prize for it. Surprising, isn't it? And why should he look for hydrogen? We couldn't find it. He looked some more. Didn't find that, but look what he found. The Big Bang. Well, this just happens over and over and over again. And I think should be emphasized. See, we must explore. We must be willing to differ with other people. We've got to be careful. We don't want to make mistakes. We don't want to do something that's stupid. On the other hand, we've got to be willing to take chances. Be willing to take chances and do some things that maybe other people don't believe in. We've got to think about it carefully and do it, explore, use new techniques, look more carefully, do everything. And if you're exploring carefully, you may not find what you're looking for, but you may find something very interesting, surprising. Surprises are all around us. We've just got to explore and find out more. Now, what more should there be? What more might there be out there? Well, who knows? That's just what we don't know. There are clearly a lot of things we don't understand. That's clear. But I'm sure some things there that we don't understand them. And we don't know that they're not there. We don't know that they are there. And we must look and look. And this is the one thing about SETI. Now, I'm not working on SETI, but I certainly encourage people to do so. Keep looking. Do the best you can. Use very sensitive techniques. Look very carefully. Maybe you won't find some people, but who knows what you'll find. Maybe you will find some people. We don't know. So let's look and be open-minded and do what we can. Now, what are the possibilities of life out there? We don't know, we can't know. We don't know how life began on Earth. It apparently began only once, because we're all related. All life on Earth has similar sort of left-handed molecules. Molecules can be right-handed, left-handed, they're equally proficient. And why aren't the right-handed types here? Well, I think that says that life probably only began once on Earth. May have begun twice and the other died out, but if it forms easily, there should be both types here, and there aren't. How did it begin? We don't know. We don't know, but boy, if we find something out there, that'll wake us up. If we don't find some things out there, that'll also tell us some things. And what about suitable planets? This planet is quite unusual, yes. Having the right kind of climate, and water and atmosphere and so on. How many other planets are there like this? Well, we don't know, but again, we ought to find out and see. What about other forms of life? Can life have completely different forms? Maybe. Maybe life can go use a very completely different kind of chemistry. Not only different kind of creatures, but completely different kind of chemistry, mechanisms that form life. Living instead of oxygen on something else? Who knows? So what might be found out there? I don't know. Will you find life? I don't know. But I think we should look. I think we should look. And looking hard and open-mindedly and sensitively and working hard, that's the way to find things. I think we should all be open-minded, explore, and that really pays off. Now it's hard for our administration and hard for industry to sort of put a lot of money into things that can't be predicted. Of course, they want to pay for something that's going to pay off. And they try to figure it out numerically. Well, if we invest in this, is this going to produce something? With new ideas, you can't predict that. And this is one reason research is difficult in getting supported. Because you can't predict that the outcome is going to do something good. Some kinds of research, sure, just developmental things and so on. But things that are new and unknown, you don't know. On the other hand, as an economist at MIT who's calculated the payoff of research, the payoff of exploration, it's enormous. The amount of payoff in industry and so on in our country and other countries, the payoff of basic research has been enormously high. And you can show that. And yet it's difficult, still difficult, to support exploration because we don't know what's going to happen. You go to a politician or a businessman and say, look, you ought to support this because it'll do something good for us. Well, just what it's going to do now? You say, well, we don't know. And maybe it won't do something. But if you do more than one thing, look in several directions, some of them are going to pay off. And they have in the future, and they will they have in the past, they will in the future, and we've got to explore. And now, as I say, I think I wanted to give a number of sort of personal experiences, because these things are hard to believe. You live through them personally, as I have, and many of them. I've seen many of my friends have done wonderful things, and live through them, you see. But new things unexpected, predicting what's going to happen in the future, who knows? But if you look at the past and history, you find that exploration does pay off. So let's all explore. Thank you.
If you have questions for Professor Towns, if you'd raise your hand and I'll give you the mic.
Charlie, that was great, and it's great to hear the examples where persistence did pay off, but you remember the ones that succeeded. What about the ones that didn't? Have there been equally bright people whose thesis projects failed and who got on the wrong track and who lost their way?
Well, you know, I can't remember any of those. Many theses have failed, and explorations have failed. But generally, as a result, people head off in a little different direction that guides them to, you see. And they find something. So I think even people who fail in one direction, that doesn't mean a failing life. That enables them to develop techniques and ideas and so on, and see something else, move off in another direction and discover something. That's typical.
That was a great talk. Thank you. I wonder if you might comment on the phenomenon of evidence being rejected for long periods of time, decades or even longer, because of it not being understood how something could possibly work. And the kinds of things I'm thinking about is the evidence, the geological evidence for the great antiquity of the Earth being rejected because we didn't understand how the sun could be putting out energy for that length of time. Mm-hmm. The rejection of the idea of continental drift because we hadn't yet discovered plate tectonics and that kind of thing.
Well, I think you've given very good examples. I'm not sure I could beat that, but that's the case. That's the case many times that we reject things, and we're still rejecting things we don't understand, and we've got to be open-minded.
I think that's something that you keep coming back to in your talk. That is the center, the fabric of this, and that is that open-mindedness. Could you speak more to what you mean by open-mindedness and evidence for it getting stronger in our culture and weaker in our culture so that we can understand in a framework better how that works?
Well, you know, I think in a way, experience and success and so on gets us in a rut. And I think older people, for example, are less likely to be creative than younger people in the long run. Sure, some older people are creative and they've been creative all their lives, they continue to be, but we get in a rut. We get fixed in our ideas. And our society gets fixed in our ideas. So we need younger people and new ideas and new things. And I think one of the great things about America, the new people immigrating here and all kinds of new things, we're not so fixed in our culture. And I think that's one thing that's helped us. Now, a very successful business, for example, frequently gets very fixed. I was once asked to advise General Motors, form a committee to advise General Motors on some problems they were having, and I formed a scientific committee and we advised them, and after about 3 years, told them, well, I think I've done enough now. So well, would you come on our board? Well, okay, so I went on the board of General Motors, and I pushed on them. I knew they were so fixed, and they'd been so successful for so long. They were fixing their ideas, and I could see things they ought to do, and I kept pushing on them, but I couldn't get anywhere much. They were perfectly pleasant to me, but no, I didn't understand. They knew things. They'd been doing them for a long time. They knew things and so on. Well, look at General Motors now, you see. They weren't completely right. You've got to be willing to change. You mustn't get stuck in a rut just because you've been successful and keep going ahead. We need new people and young people too.
I want to, since you're reminiscing about General Motors, I want to ask you to continue the personal reminiscing. How did winning the Nobel Prize change your life? Did Berkeley teach you any differently? Did a lot of new people approach you? Reminisce, if you would, a little bit about what happened after the Nobel Prize.
Well, the Nobel Prize complicates your life. Not that I wouldn't accept it, but nevertheless, after you get asked to give talks, for example. In general, a lot more public relations you have and so on. Well, those are important, I think, for scientists to have public relations is important. And it has complicated my life. But also, it's been helpful. It's been helpful in many ways. And There are very few people who've turned down the Nobel Prize. It's generally very helpful, even though it is complicating, and that it makes you more of a public figure, and a lot of things, extra things you have to do, and so on. But doing those things publicly is some importance also.
Charlie, thank you very much for this talk. I would be interested if you have any comments on the boundaries between religion and science. I think those of us who work in science and have watched what's happened in a more conservative administration over the last 8 years have been rather appalled at some of the decisions that have been rendered from on high in the political process when you had a conservative, very religious president. And I think it's going to be part of the future of the United States and the future of science here in the U.S., and I'd be interested in your comments.
Well, I myself am religiously oriented, but I'm not a fundamentalist. And I think science and religion are much more closely related than we recognize. And they tell each other something. For example, Einstein couldn't believe that the universe had a beginning. Oh, it couldn't have a beginning. That's ridiculous for it to have a beginning. Well, we now know it did have a beginning. It did have a beginning, and that shed something maybe on religion. How did it begin? But it had a beginning, a unique beginning. Now, in addition, science tells us something about how people work. What makes a good life, what makes people work, and so on. And I think as we discover more and more in science, we discover more and more surprises and recognize more and more very difficult to understand things. There are lots of inconsistencies in science, as well as seem to be inconsistencies in religion. I think there are fundamentalists in science as well as fundamentalists in religion who believe, oh, this is exactly right, I know exactly what's right. We've got to be open-minded in both fields. Got to be open-minded in religious areas, open-minded in scientific areas. And the two, as I say, they can shed light on each other to a certain extent. And will continue to do so, and I think increasingly so, as we discover more and more and as we understand more and more in both fields.
Professor Townsend, the United States has now committed itself to going back to the moon, and in the next decade hopes to have men back on the moon. Can you tell us a bit about your role in the Apollo project and any lessons that you may have for the Constellation project that the U.S. is now?
Again, the Apollo project was one of those things that was a surprise to many good scientists and engineers. It was announced, of course, by the president. And NASA appointed a guy named George Muller to run it. Well, I'd happened to know George Muller when I was a student. I knew him pretty well. And the whole project was being very strongly criticized by a lot of outstanding engineers and scientists. Vannevar Bush, for example, MIT, very famous guy, he was absolutely against it. When I became provost at MIT, and well, I'll tell you a little bit more about that later. A lot of people were against it. Very outstanding scientists, characteristically scientists and engineers were against it. Not very practical, not worthwhile, and so on. Well, I ran into George Muller on the street, and I said, look, all these people are criticizing the project. You ought to get together with some of them. Maybe they have some problems to point out to you that you ought to know about. Maybe they ought to know about what you're doing and understand better about what the possibilities are. You ought to get together with them. Oh, he said, well, he called me up a week later and said, well, Jim Webb, who was then head of NASA, said he thinks it's a good idea. We'd like you to get together a group of them and be chairman of the committee. Uh-oh. I wasn't very eager to do it. Well, I felt, well, maybe I ought to do it. So I called up a lot of these people who were outstanding scientists and engineers, but most of whom objected to the program. And all but one of them agreed, well, okay, we'll consult with George Miller and try to tell him what we think ought to be done. All but one, John Pierce, a very famous electrical engineer at Caltech. I called him up and John said, look, I've always figured something's not worth being done, I won't have anything to do with it. So he didn't, but everybody else did. And we got these guys together and talked with George Miller. George Miller met with us each meeting. He met with us and talked with us and listened, and they listened a bit to him and so on. And after about 6 or 8 months, these people said, "Oh, maybe we can make it work." And they began to get really interested, and they worked on it, and I think they helped a lot in giving him advice as to what to do. And he listened carefully. He was very interactive and listened carefully and thought about it, and worked on it. And so we kept working on it, and these people began, "Oh yes, look, we think we see how it really can work," and they gave him good advice. Good advice. They were outstanding people. And lo and behold, the Apollo program came in on time and under budget. Now, Van Bush, I'd gone to MIT as provost when I ran into George Miller and agreed to do this. I agreed to be this committee. Van Bush said, "Oh, look, you're absolutely crazy. You know that can't work. It's going to take 3 times longer than they say. It's going to cost 10 times more," and so on. That's a crazy thing to do. You're just a big mistake to do that. Well, I went as provost, and they told me if you come as provost, you'll probably become president of MIT and so on. I went there, and I wasn't president of MIT, and Van Bush was the chairman of the board. I think I know why I wasn't, but that's good. You see, now that particular failure, that was great because that led me to do something else. I came to California to do astronomy, and that's great. I much more enjoy that. You see, failure becomes a success in many cases. So Van Bush was absolutely all against it. And it came through under budget and on time. Now, not many government projects do that. And it came through, by then I'd left MIT. But Van told me, say, "Well, that's just very surprising and great. Congratulations." So he eventually turned around. He had to.
What do you think about a return to the moon, which was the second part of that question?
Yeah. Do you have any views on our return to the moon?
On the present one, I'm not so certain. I haven't looked at that carefully. I think the question is, sure, we can do that. How much good will it do? Is it worth the money and the effort? It's not clear to me. Sure, it'd be interesting to do that. Is it worth the money and the effort? Now, the first project, people questioned whether it was worth the money and the effort. Turned out to be enormously successful, made a big difference to the position of the United States in the world, and a big difference to our technology and so on. It was just great. But that was a breakthrough. A second trip to the moon is not exactly a breakthrough. And so I don't know. I don't have any very firm opinion about it, but I'm not enthusiastic about it, I would say.
And how about Mars? I heard the question too.
How about Mars? Oh, I think we certainly should explore Mars. Now, sending a person to Mars, that's different. But we can explore Mars technologically to a great extent. We certainly ought to do that first. And depending on what we find there, we may decide we ought to send somebody there, but that's an enormous job. So we can do it with equipment. And we are doing it, of course, and that's just great. We want to find out what's there, and that'll tell us a lot. And, of course, we may find something fantastically interesting, but we may find out a lot, but tell us, well, there's no life there. That's different.
Do you have any insights in the gap between the Shuttle program and the Constellation program? It looks like several years we're going to have to be hitching rides on Russian craft to get up into space.
I don't think I have any useful comments on that, really. I haven't looked at that closely. I have not been very close to the space program in recent years, and I don't think I can make any useful comments there.
In a perfect world where our young scientists had unlimited funding, is there any research that you would recommend?
Any research? All research. But of course, well, biology, of course, is a fantastic field now. Biology is becoming more fundamental. When I was a youngster, my brother was a biologist. I thought of going into biology. But biology was simply descriptive then. You name the plants and animals and see how they, what they were like and so on. But it was descriptive. Now it's gotten down to fundamentals. And so it's much more interesting. And I think today I might go into biology, or biophysics or something. Physics and biology coming close together, you see. So I think biology is a fantastic field. Of course, astronomy is a fantastic field. Lots to be found out there. And there are many others. Nanotechnology, for example, technologically is fantastically interesting and potential, lots of potentials there. So there are many fields. But I would say if you picked out a single big field, I think I would pick out biology and astronomy as the sort of the two most challenging and interesting at the moment.
Professor Towns, you mentioned a couple of your students who've now gone on to make a name for themselves. Do you have any guiding rules or things that you try to do with students as a mentor that that you feel enabled them to spread their wings a little more effectively?
Well, I think just simply having students do challenging things, learn as much as they can, do challenging things, and be open-minded. And I think we all need to, let's don't get into a rut and just specialize on one thing. Look at other fields. Look at fields broadly. Look at other fields and learn as much as you can, and do challenging things. I think that's a good stimulus for students. Be willing to take chances and do challenging things and learn things. Learn as much as you can.
Charlie, you've had just a fantastic career for 70 years plus or minus, and I'm curious about any comment you have about optimistic versus pessimistic views of where our world is, where our research is going, and did you have ups, did you have downs? And then I'm also interested today, are you optimistic or pessimistic about the future?
I've always been somewhat optimistic. I recognize, yes, we've got big difficulties. We've got very big difficulties. We've got to struggle against them. But on the other hand, the potentialities out there are enormous. And I'm generally optimistic. If you look at the history of humans, certainly we've been steadily developing. And I hope we can continue to that. Now, of course, we can destroy ourselves. That's possible. Nevertheless, even if we have some atomic bombs and kill 5 million people, let's say, still a lot of people left. And I think we'll keep going. And I hope we won't have any such thing. And I think we've got to work very hard on that. See we keep going. Now, in the long run, how far will we go and what can we do? Well, we're beginning to see how to form life artificially. Will we be designing people? Should we design people? We have a lot of big questions there. A lot of big questions as our potentialities develop more and more. We'll be living longer. We can plan how a child should be designed. We'll be able to do that more and more. Should we do that? There are very big issues there, very big potentialities. Well, I think to guarantee that a child won't be crippled or something like that, well, that's good. But try to say, well, no, I want my child to have legs that are an extra 2 feet long so he or she can win the Olympics. And design a child that way, I'm not so sure. But we've got a lot of potentialities ahead. I think we should be optimistic, but primarily we should try very hard to see that good things happen.
Charlie, the Large Hadron Collider gets turned on today. A lot of people were really unhappy when the superconducting super collider didn't go forward. How do you see the United States' place in the world of scientific research globally, and do you see it changing? And if it's changing, do you think it's changing for the good, for the bad, or it's just okay?
Well, of course, we are not as outstanding compared with other countries as we used to be. In a way, that's good. I think it's good for other countries to do good things too. But I think that shouldn't slow us down. I think we need to work hard, and we ought to try hard to be on top as much as we can. But it's good for other countries to be doing good things also. I'm delighted to see the Hadron get going. And it'd be very interesting to see what, if anything, they find. I'm sure they'll find out something that's different, but whether they find what they expect or find that it isn't there, I don't know. Or find something completely different. But we'll see.
Okay. If you join me in thanking Professor Towns for his fantastic